Good morning, everyone. I'm Wentao from the University of Hong Kong, and today I will present our paper on an LLM-driven agent-based framework for evaluating cross-regional construction policies in the Greater Bay Area. And this is the structure of the presentation. And let me start with the background and the research gap. The Greater Bay Area is designed as an integrated city cluster, so construction collaboration is increasingly not limited to one city. Projects may involve owners, consultants, contractors, and regulators from different jurisdictions. At the same time, cities play different roles. Some are regional hubs, and some are manufacturing or supply chain bases, and some are emerging peripheral markets. Policy pilots such as filling and mutual recognition mechanism try to reduce the institutional barriers. However, the impact of these policies is difficult to observe before implementation. Real-world experiments are slow and costly, so we need a traceable simulation sandbox to test how policy changes may reshape the collaboration. But existing approaches still leave two gaps. The first is limited behavior traceability. Macro models such as CGE or system dynamics can describe aggregate policy effects, but they do not clearly show how different construction actors interact, remember past experience, and adapt to new institutions. And the second is weak policy traceability. Traditional rule-based ABM can represent actors, but it often depends on predefined rules. When decisions depend on project stage, workload, partner history, and policy friction at the same time, the rule system becomes difficult to scale. So the needed capability is a framework that is process-aware, policy traceable, and adaptive. So based on this gap, the objective of this study is to develop a traceable simulation testbed for evaluating cross-regional collaboration policies in the Greater Bay Area. Now I move to the methodology and technical framework. This slide shows the overall macro-coupled IBM framework of this work. There are three connected layers. On the right, the project lifecycle backbone defines how projects move from init, scheme, award, and deliver. On the left, agent modeling describes how stakeholders perceive the environment and use the memory and strategy select actions and receive feedback. At the top, the macro environment and policy module provide market demand, price pressure, regulatory intensity, and policy parameterization. The important point is that micro-level project decisions and macro-level industry conditions are coupled. Agent action create project outcomes and collaboration ties, and this outcome feedback into the environment over time. A key design principle is executable. Each project follows a fixed four-stage state machine here. Transitions are controlled by hard gates, such as whether the brief is ready and whether the scheme is frozen, and the contract and safety plan are completed and handover is closed. The LLM agent is therefore bounded. It receives context, memory, and policy constraints, but it can only choose from the admission action set at the current project state, and then the simulator executes the action, updates states, and logs outcomes. This framework includes 7 stakeholders here, and the LLM is used for context-sensitive action selection, but the system is hybrid rather than purely generative. The system pipeline starts from the perception, culture, strategy, and memory. These are packaged into a structured prompt together with raw instruction and feasible actions. The LLM then selects one feasible action and give a short rationale. After that, the rule-based action and give a short rule-based simulator checks feasibility, executes the action, updates the policy states, and write outcomes back into the memory. This keeps the agent behavior realistic, auditable, and executable. And the next component is policy parameterization. Instead of using policy tags only quantitatively, each policy is encoded into a policy vector here. The 5 parameters are entry waiting time, approval success probability, procedure uncertainty, compliance burden, and the scope breadth. This parameter enter the model through these 3 channels, and this create a traceable mapping from policy provisions to agent behavior and simulation outcome. After building this framework, the next question is whether the simulation is credible. In this section, I will show validation through Stylized-facts and then use the validated platform to discuss policy zone effects and cross-border collaboration patterns. For validation, we aim to test whether the model can reproduce robust stylized facts in the construction industry. The first concentration with head firm dominance. The simulated CR10 trajectory shows an upward pattern that is consistent with the national concentration trend. And the second is distance decay with local buyers. The simulated contract records show that the collaboration becomes sparser at longer distance, while local and nearby collaboration remains dense. We also ran ablation tests. The full model performs better, removing memory weakens the fit and removing intra-row heterogeneity weakens its feeder. This suggests that memory and heterogeneity are important to reproduce the realistic dynamics. After validation, we analyze cross-regional policy effects. At the city level, the mainland GBA network does not expand uniformly. Instead, it develops a core, semi-core, and periphery structure. Guangzhou and Shenzhen show broad collaboration capacity. Foshan and Dongguan are more connected through manufacturing and supply chain. This is why cross-border collaboration is important in the GBA area. And the model also reveals important Hong Kong and Macau collaboration characteristics. First, the mobility is directional. The net inflow from Hong Kong and Macau to the mainland is stronger than the reverse, especially through Qianhai and Hanqing. Second, sensitivity analysis shows a nonlinear response to policy parameterization. Reducing waiting time creates deep gains when delay is already low, while approval success shows diminishing marginal effects. Third, the Qianhai gateway effect is robust. Even a modest friction advantage increased the share of Qianhai link cross-border projection, although the marginal gains flatten as the advantage become larger. And this is our takeaways here. Thank you very much for your attention, and I'm welcome to your suggestions.